Analavos of the great hypersigil. Let's describe what can't be described.
Let's start with power sets.
So again, it's a contradiction. So when I was teaching at Oxford, one of my students came up with the following different anthropomorphization of Cantor's argument. Let's consider all possible fruit salads. We have a given collection of fruits, apples and oranges and grapes, whatever. And a fruit salad consists of some collection of those fruits. So there's the banana, pear, grape salad, and so on. There's a lot of different kinds of salad. Every set of fruits makes a salad, a fruit salad. Okay. And we want to prove that for any collection of fruits, even if there are infinitely many different kinds of fruit, for any collection of fruits, there are more possible fruit salads than there are fruits. So if not, then you can put a one-to-one correspondence between the fruits and the fruit salads. So you could name every fruit salad after a fruit. That fruit might not be in that salad. Doesn't matter. It's a naming, a one-to-one correspondence. And then, of course, we form the diagonal salad, which consists of all the fruits that are not in the salad that's named after them. Mm-hmm. And that's a perfectly good salad. It might be the kind of diet salad if it was the empty salad, or it might be the universal salad, which had all fruits in it, if all the fruits are in it, or it might have just some and not all. So that diagonal salad would have to be named after some fruit. So let's suppose it's named after durian, meaning that it was associated with durian in the one-to-one correspondence. And then we ask, well, is durian in the salad that it's named after? And if it is, then it shouldn't be. And if it isn't, then it should be. And so it's, again, the same contradiction. So all of those arguments are just the same as Cantor's proof that the power set of any set is bigger than the set. And
a whole. Aleph null is the smallest countable infinity, and it's equal to the size of the set of natural numbers. The size of the set of real numbers is 2 to the power of Aleph null. Beth null equals Aleph null, which is the size of the set of natural numbers. Beth 1 equals 2 to the power Beth null, which is the size of the set of real numbers, and Beth 2 equals 2 to the power Beth 1, which is the size of the power set of the real numbers. So in general, Beth n plus 1 equals 2 to the Beth n.
And now for causal entropic forces.
So what you've just seen is that a variety of signature human intelligent cognitive behaviors, such as tool use and walking upright and social cooperation, all follow from a single equation which drives a system to maximize its future freedom of action. Now, there's a profound irony here. Going back to the beginning of the usage of the term robot, the play R-U-R, there was always a concept that if we developed machine intelligence, there would be a cybernetic revolt. The machines would rise up against us. One major consequence of this work is that maybe all of these decades we've had the whole concept of cybernetic revolt in reverse. It's not that machines first become intelligent and then megalomaniacal and try to take over the world. It's quite the opposite, that the urge to take control of all possible futures is a more fundamental principle than that of intelligence, that general intelligence may in fact emerge directly from this sort of control grabbing rather than vice versa. Another important consequence is goal seeking.
And now for the universal set, the null set, and gauge symmetry.
Universal set. A set large enough to contain all sets under consideration in the current context. Universal set synonyms: universal class, universe. UNIVERSALSET. Universal set.
Hi, for this video what I want to do is talk to you about empty and universal sets. An empty set is also known as a null set sometimes, is a set containing no elements. That means that there is nothing in it. It could be a situation as described and there's nothing that matches it. But anytime you end up with something that is empty, it's denoted by either a circle with a line through it, or you can use the set brackets with nothing inside. So these are the two ways that are used to denote empty sets in mathematics. So an example could be rolling a 7 on a die. This would result in an empty set because when you're rolling a die, you can only end up with the numbers 1, 2, 3, 4, 5, or 6. And so like if you were looking for the probability of rolling a 7, that would be 0 because there aren't any. Your result is a empty set because there is nothing that matches that. Okay. The other one that I want to talk to you about is a universal set. A universal set will change from problem to problem. It's the set that contains all of the elements for a specific situation or a given problem, and we denote it by the capital letter U. So a couple examples that you might encounter would be all the letters in the alphabet. So if you ended up with a letter that was in the alphabet, then it would be contained in your set. If you ended up with something like, say, a number, then it would not be contained in that set. Okay. Another example would be the numbers 1, 2, 3, 4, 5, 6. This would be the set of all values that can be rolled on a number, or on a die or a number cube, as they sometimes call it in some textbooks now. But it's just the numbers 1, 2, 3, 4, 5, 6. Another example could be the set of all real numbers. So it really does change from problem to problem. So a universal set is dependent on the information that is given to you. So a lot of times it will be given to you in the directions. It will say for this set use this universal set, or for this set it has to be a real number. So if it's not contained in there, then it would result in an empty set.
And then there's one very special example of a set I'm going to illustrate. It's the set with nothing in it. Squiggly brackets with nothing. This is an empty box. And we give a special symbol to associate to that set with sort of 0 with a backslash to it. This is the empty set. Now, I should note that mathematicians do actually go a bit further than just agreeing as this is a foundational concept. There's a list of axioms that specify the different properties that sets have to have. The Zermelo-Fraenkel axioms are the most standard way that mathematicians have agreed on the basic concept. But either way, we're saying this is the base, and we're all just going to agree on what that means. Okay, so let's do something with that. I want to now interpret what is a number, because a number is not a set. I've talked about the set that contains numbers, but what really is a number? Could I interpret numbers as just being a special type of set? So basically what I'm going to do is I'm going to look at the natural numbers, 0, 1, 2, 3, and so forth, and try to associate a particular set to each of them. So the first one I'm going to do is I'm going to associate 0 with the empty set. I'm drawing an arrow here relatively loosely, and what I'm trying to say is that the concept that you and I have in our minds of 0, I'm going to interpret that in terms of the language of set theory by associating to it the empty set. Indeed, the empty set is not nothing, it is a set with nothing inside of it. And so this association makes sort of sense because I'm associating 0 with the set that has 0 elements inside of it. Likewise, let me take the number 1, and 1 is associated to a set as well. It's associated to the set with 1 element in it. The element is just the empty set. So I think of this as a box, that's the big outside set, that contains the empty set. This is a box within a box. Okay, let me keep going. What about 2? 2 I'll define to be a special type of set that has 2 different elements into it, so let's make this different association. 2 is the set that contains, well, both of the previous ones. It contains the empty set, and it contains the set that contains the empty set. So in other words, at the level of the outside box, this biggest box, there's 2 things inside of it. There's an empty set, an empty box, and then there's a box that contains an empty box. There is the set that contains the empty set. Okay, so
if we have something that has a value at every location in space and time, this is called a field. So this information that you add, that's what's called the gauge field. Gauge phases field moving electrons what? Bear with me, I have an example. Suppose you have an old-version beam balance. If you have the same length of beams on both sides and the same weights, it's in balance. Now let's say that adding weights is like shifting the phases by an arbitrary amount. If you add the same weights on both sides, nothing changes. This is like saying the physics remains invariant under this arbitrary choice if it's the same in both places. But if you add a bigger weight on one side than on the other, that ruins the balance. This is like setting a different phase in one place than the other. This is your gauge. But that'd mean the physics depends on this arbitrary choice. Not good. So what you do is that whenever you add a weight, you also adjust the support of the balance arm. This is what the gauge field does. If you change both together, you always keep the balance. With the gauge field, the gauge doesn't matter. This is basically how gauge symmetries work. You tie two changes together so that the net cancels out. And you do this because quantities which are physically measurable shouldn't depend on arbitrary conventions. We think about light. Yeah, so the thing is that once you introduce this gauge field, it develops a will on its own. It's there to keep the electron phases properly lined up. But it can do things even if there's no electron inside anywhere. In particular, it's got ripples that can travel, and those are the photons, the quanta of the electromagnetic field. They are what light is made of. Again, this is very similar to Einstein's theory. Space curves around masses. But even if there are no masses, space can have ripples that travel. In Einstein's theories, these are the gravitational waves. For the electron, they are electromagnetic waves. So this is why we have light, because we have electric charges. Another thing that you can learn from this is that you can't have an electron without an electric field. You knew this already, but I think it's a somewhat underappreciated point because it means that this electron in the STEMNAT model chart, it doesn't exist. We've never seen it. The electrons that we actually observe, they always have a cloud of photons around them. This idea is called gauge symmetry. So we have light because we have electric charges. You might then ask, well, why do we have electric charges? Physicists don't have a good explanation for this one. They've certainly tried. They've tried with unified theories and theories of everything, but none of those have really worked so far. Personally, I think the reason we have electrons is because it's the simplest particle you can think of. It comes from the simplest symmetry there is in all of mathematics, just this one phase. Indeed, getting the electrons and the light with them is the easy part. The difficult part is explaining all the other properties of the STEMNAT model. But regardless of how you look at it, gauge symmetries are how nature works. And that's why light exists.
Our external physical reality is a mathematical structure. That is, the physical universe is not merely described by mathematics, but is mathematics, specifically a mathematical structure. Mathematical existence equals physical existence, and all structures that exist mathematically exist physically as well. Observers, including humans, are self-aware substructures. In any mathematical structure complex enough to contain such substructures, they will subjectively perceive themselves as existing in a physically real world.
Thank you for walking down this mathematical journey with us. Hey!